This illustration captures the messy reality of asynchronous data processing. The prompt is to build a system that ingests millions of overlapping records flowing into a black box, ensuring duplicates are never processed, even if they arrive minutes, hours, or days apart. This chart shows the exact step-by-step translation from that vague prompt into a structured distributed systems pattern. You achieve global deduplication by breaking the problem down into 4 distinct components: an idempotency key store, a durable processing ledger, a TTL-aware storage layer, and an asynchronous processor. Looking at the right side of this diagram, you establish the strict target metrics required to make this pattern work. We target an average throughput of 1 million records per minute, and a strict requirement that our decision latency stays under 100 milliseconds. We also maintain a 30-day retention window. Defining these precise boundaries up front prevents designing a system that works perfectly on a whiteboard but collapses under actual production loads. Every architectural decision from this point forward will be dictated by that 100 millisecond latency target and that 1 million record throughput. The most common trap engineers fall into when approaching this problem is the read-then-write pattern. They query the database to check if a record exists. If it doesn't, they write it. But under heavy load, 2 concurrent duplicate requests will both read not found at the exact same time, both write to the database and trigger double processing. This diagram outlines the core abstraction. We rely exclusively on an atomic conditional insert, ensuring the first writer wins and rejects duplicates. Look at the highlighted formula. Hashing the tenant, source, and record ID ensures every duplicate resolves to the exact same string. By offloading the resolution of the race condition directly to the database's atomic constraints, you guarantee absolute correctness. You avoid having to build complex application-level locking mechanisms, which are prone to failure and difficult to scale. This diagram maps out the high-level system architecture, and you can see a clear dividing line in the middle. We separate the design into a synchronous ingestion path that executes in under 100 milliseconds and an asynchronous processing path that handles the heavy lifting via message queues and background workers. Let's walk through the happy path for a first occurrence record, shown here in 5 phases. The system ingests and validates the payload, generates the unique hash key, and successfully executes the atomic claim in the database. Finally, it persists the payload and publishes the task to the event queue for worker processing. Now look at what happens when an eventual duplicate arrives days later. The system generates the exact same hash key, but at step 3, the database's unique constraint blocks the entry entirely. The system updates the metadata to reflect the retry, and the flow halts immediately, preventing any downstream processing. This flowchart illustrates the critical failure state known as the dual write problem. Look at the top section labeled Without Outbox. If the database insert succeeds at step 1, but the system crashes before publishing to the message queue, you generate a permanent ghost record. The database has claimed the key, blocking future retries, but the processing instructions never reach the workers. Shift your focus to the bottom section, labeled With Outbox pattern. We solve the ghost record problem by opening a single atomic database transaction. We write both the record data and a pending event row to an Outbox table simultaneously. If the system crashes, a background reconciler constantly scans the Outbox for pending events and safely publishes them to the queue. You cannot cross the boundary between a synchronous database commit and an asynchronous message queue without risking data loss. The Outbox pattern provides the essential bridge to guarantee that every claimed record is eventually processed. This equation breaks down the reality of exactly once processing. True exactly once delivery across distributed networks is nearly impossible. Instead, the production standard combines an at-least once queue, an atomic deduplication claim, and an idempotent worker to achieve what we call effectively once processing. Let's test this architecture against a severe edge case. Imagine a malfunctioning upstream webhook suddenly fires 1 million identical duplicate requests per minute. If you allow that entire barrage to hit your primary database, the sheer volume of constraint checks will exhaust your connections and melt the storage layer. This diagram shows the defense mechanism, the hotkey mitigation strategy. We deploy a Redis negative and positive cache with a very short time to live in front of our main storage. This acts as an optimization layer. When the duplicate storm hits, Redis absorbs the millions of retries and rejects them in memory, long before they can touch the durable database. This trade-offs matrix compares our options. A pure Redis approach lacks strict correctness and risks data loss on eviction. A pure SQL approach provides correctness but struggles with high-volume hotkeys. The hybrid setup in the right column gives us the fast common path for absorbing traffic spikes while maintaining the durable database as the absolute source of truth. Senior system design requires layering these specific defenses. You rely on fast, volatile memory to protect the application scale, and you isolate the slow, durable database to ensure absolute correctness. This failure map tracks how we mitigate downstream errors. If a worker crashes mid-processing, queue timeouts ensure the message reappears for a safe retry. Further down, poison messages that consistently crash workers are safely routed to a dead letter queue. Operating blindly is dangerous, which is why an observability suite is required. This dashboard tracks 3 vital signals: P99 decision latency for our 100 millisecond target, database conflict rates to detect high contention, and the Outbox pending count indicating publisher failure. This blueprint summarizes our architecture. Principle 1 establishes the abstraction using deterministic keys. Principle 2 relies on atomic database constraints as the source of truth. Principle 3 deploys the Outbox pattern for reliability. Finally, Principle 4 uses Redis caching to absorb duplicate storms. In an interview setting, throwing out names of databases or queue technologies doesn't prove seniority. Defining failure states, anticipating edge cases, and combining distinct patterns into a cohesive blueprint proves you can build a bulletproof production-grade architecture.